Hello and welcome. In today's lecture, which is likely to be slightly longish, we are going to look at the analysis and design of dynamic systems, particular focus on seesaw feedback control loops. Here is a standard seesaw feedback loop. The process, this is the process. You can't change this. This is what it is. So there is a disturbance that affects the output, and there is a control input that affects the output. We are interested in the output being at or close to the set point, and the idea behind feedback control is you get the deviation away from set point and then on this error signal the controller operates and makes the necessary calculations to output the movement in the control valve or the control input to the process. So this is a standard seesaw feedback loop, and we have seen previously that if you do the block diagram algebra, we get y is equal to whatever is in the forward path divided by 1 minus whatever is in the backward path. So eventually it becomes plus because of this minus sign. Whatever is in the forward path divided by 1 plus GPGC times D. So this is the resolved block diagram, and the resolved block diagram is shown here, and this is the servo transfer function, this is the regulator transfer function, and you can see that the denominator of both the transfer function is 1 plus GPGC, and the roots of the polynomial in the denominator are the roots of the characteristic equation. So the characteristic equation for the closed loop system is this guy, and GC is typically a PID controller, and if you look at a PID controller with the D action in there, you will see that in terms of deviation variables, so there's no bias term, is Kc times E plus 1 by tau I times integral of error till current time plus this is what, and if you take the Laplace transform of this chap, you will get U is equal to Kc times 1 plus 1 by tau is plus tau d s times E, and this will give U by E is equal to divided by tau is times Kc times tau I tau d s square plus tau I s plus 1. This is the transfer function that we get, and you can notice that the numerator order is greater than the denominator order, so this is not physically realizable. This is not realizable because numerator order m is greater than denominator order n, and therefore what is done is different variants are used for approximating the derivative action, because perfect derivative is physically unrealizable, and this order is greater than that because of the derivative action, because of this term. And so what is done is in practice the most commonly used PID controller transfer function is this guy. This is the standard PI controller, and then you add a lead lag which is lead dominant. This is a lead lag which is heavily lead dominant, Heavily lead dominant means alpha is much less than 1. So typical value of alpha would be, for example, it will be in the range 0.05 to 0.1. I typically use a value of 0.1. So alpha is 1 by 10 or 1 by 20. Yeah. So that's a lead dominant transfer function, a lead lag that is applied to the PI transfer function, and this is an approximate PID controller transfer function that we shall be using, that is usually used, very commonly used. Okay. Now when we are designing a control system, we have a dynamic system, and a dynamic system can be analyzed for what kind of a dynamic response it has, or you could design your controller so that the dynamic performance of that controlled process satisfies a certain performance specification. Of course, that performance specification must be feasible, realizable. So what is analysis? Given a dynamic system, what are the dynamic response characteristics? And the dynamic system in general could be with control or without control. So that's analysis. So problem may be, for example, I've given a tuning, or what is the characteristic equation? Is this the characteristic, is it stable or unstable? That's characterization of the dynamic response. Given a transfer function, what is the rise time, peak time, blah blah blah, decay ratio, and so on and so forth. Design, on the other hand, you have a certain desired closed loop response characteristic, and you want to obtain that response characteristic through proper choice of Kc, tau I and tau d, your controller tuning parameters. So you design your tuning parameters to satisfy dynamic performance criteria. Now metrics that characterized the closed loop response could be in the time domain, could be in the Laplace domain. In the time domain, you got things like rise time, peak overshoot ratio, damping ratio, and so on and so forth. In the Laplace domain, you got the closed loop damping coefficient, and we know that the damping coefficient has a relation with things like damping ratio, peak overshoot ratio, peak time, rise time, and so whether you're specifying damping ratio, peak overshoot ratio, peak time, rise time, settling time, or you're specifying closed loop damping coefficient of the dominant pole pair in the Laplace domain, these are equivalent. For example, we know that, I don't remember the expression, but e to the power minus pi cot phi. I thought that this was the peak overshoot ratio. So if peak overshoot ratio is specified in the time domain, then this equation gives you phi, and once this equation gives you phi, we know that cos phi is equal to the damping coefficient. So whether you're specifying peak overshoot ratio or you're specifying damping ratio, there is a relationship that these metrics have with the damping coefficient, and therefore specifying the damping coefficient or the time domain closed loop response characteristics, these are actually equivalent. Okay. Now the first question in the analysis of dynamic systems that one usually asks is the system stable? How do we go about doing it? Well, the system stability is determined by the system characteristic equation roots, which, if the dynamic system has a transfer function, the characteristic equation roots are the same as the transfer function poles. So if any of the roots or poles are in the right half plane, then the system is unstable. If all the roots are in the left half plane, then the system is stable. Now we need a simple technique for how many right half plane poles are there for a dynamic system, and the dynamic system could be, for example, 10th order. And we want to do this without calculating all the roots, even though there is a MATLAB command called roots. You give the coefficients of the polynomial and MATLAB will calculate all the roots in the blink of an eye, and then you can look at those roots and plot them on the S plane and see which one of them are, the pole zero map, and you can see which ones are in the left half plane, which ones are in the right half plane, and if any one of them is in the right half plane, you got an unstable system. One of the techniques, it's a simple technique, the Routh array, and this technique is that technique that tells you how many right half planes are there for a given characteristic equation. How does the technique work? This is like stating the obvious. Write down the characteristic equation, prepare the Routh array, and the Routh array is an array. You look at the first column of that array. The number of right half plane roots for that characteristic equation is the number of sign changes in the first column of the Routh array. That's the key result. For a closed loop system, the characteristic equation is a function of the controller tuning parameters, such as, for example, Kc. So the Routh array therefore can be used when you prepare the Routh array. The first column elements will be a function of Kc, or at least some of those elements will be a function of Kc. Now, in order for none of the elements to exhibit a sign change, that will give a condition on Kc that for the elements to not exhibit a sign change, there is a constraint on Kc, and this constraint can be used to calculate the limiting value of Kc at which the system goes unstable. So Routh array can also be used for figuring out when does the control system, or when does a particular characteristic equation go unstable as Kc is changed. What is that limiting value of Kc for which the closed loop system, whose characteristic equation is known, goes unstable. How do we calculate the Routh array? It's actually quite simple. This is that general characteristic. Remember, we made the general transfer function, which was g is equal to well, let me see, maybe I should put it in shorthand. I like these summations. Summation j equal to 1 or 0 to m times bj times s to the power j divided by summation ai times s to the power I equal to 0 to n. So this is the denominator of the transfer function, and the denominator polynomial equal to 0, the roots of that transfer function are the poles. So the general characteristic equation is the denominator polynomial going to 0 of the transfer function, and so this is coming from here. So this is the general characteristic equation for a dynamic system. So you write down the characteristic equation. For a closed loop system, some of these coefficients may be functions of, for example, Kc. So what you do is to prepare the Routh array. Routh array is a bunch of rows, s to the power n, s to the power n minus 1, s to the power n minus 2, and what you do is you fill in the blanks, and s to the power n will have coefficients of s to the power n. What is the coefficient of s to the power n? What is the coefficient of s to the power n minus 2? What is the coefficient of s to the power n minus 4, and so on and so forth. So when you write these coefficients, what is it going to be? It's going to be an minus 2, and hang on. So maybe I should put on a j here. And what we are doing is j here is n. This row would be n minus 1, this row would be n minus 2, and so on and so forth. Will go on till j equal to 0. A n minus 4. What will come out here is a n minus 1, a n minus 3, a n minus 5, and you can keep going on. Now let us call these coefficients b1, b2, and so on and so forth. This coefficient is obtained as this multiplied by that minus this multiplied by that divided by this guy. So b1 is equal to a n minus 1 into a n minus 2 minus a n into a n minus 3 divided by a n minus 1. b2, let's look at b2. b2 is going to be, this is just a procedure, so just understandable, this times this minus this times that divided by again this guy. So b2 is going to be a n minus 1 into a n minus 4 multiplied by a minus a n times a n minus 5 divided by a times n minus 1. And similarly you can go on. If there are elements here and here, then b3 is going to end up being this times this minus this times this divided by this guy. Now once the b row is done, you come to the next row. So c1 and c2, how are c1 and c2 going to be calculated? C1 is going to be same procedure, this times this minus this times that divided by this guy. It's going to be b1 times a times n minus 3, a n minus 3 minus b2 times a n minus 1 divided by a n minus 1. Sorry, divided by b1, sorry, divided by b1. Yeah, okay. Let's say there is a coefficient here too. Then c2 is going to be, and I'm not going to write the expression, c2 is going to be this times this times this times that, and if there is no coefficient here then you treat that as 0, divided by this guy again, and so on and so forth. You keep going until you hit the s to the power 0 row, and there will be only one element in that, and that's it. So you get a triangular kind of looking array which is called the root array. And once you have the root array, what you do is, oh shucks, I removed that. It doesn't matter, you know. So this is your root array which looks somewhat triangular. What you do after you have looked at it, you look at the first row, and all these elements should have the same sign. If there is a sign change, the number of sign changes is equal to the number of right half plane roots for this characteristic equation. So just reinforcing how the elements are calculated, look at the first row. After preparing the array, number of right half plane roots of the characteristic equation or poles of the transfer function is equal to number of sign changes in the first column of the array. That's the Ruth array technique, and it is best understood through examples. So let's just, before going into examples, let's look at special cases that might arise. So when you're preparing the Ruth array, for example, you may have row I and element 1, element 2, element 3, and for example, let's say this is 2, this is 8, and this is 10. You can see that 2 is a common factor, so then this element can be replaced by 1. You can take that common factor out. This element can be replaced by 4, and this element can be replaced by 5, and that makes the multiplications smaller. So this kind of taking a common factor out of a row is allowed. So whenever you can, you should take a common factor out. Don't take -1 out, because that will mess up things. That will mess up your sign changes. So that's number 1. Number 2, sometimes what happens is, as you are preparing the Ruth array, you're filling up elements, and somehow an element, the first element of a row, turns out to be 0. Now 0 multiplied by this guy minus this multiplied by that guy divided by 0, that's going to create a problem here. So how do you proceed? There are two ways of proceeding. Number 1 is just replace this 0 by a delta, small number delta, and keep on writing your elements in terms of delta, and take the limit as delta goes to 0, and then see if there are sign changes in the first column. That's the first way. The second way is, you got this polynomial p of s equal to 0. Now what you do is, you do the substitution s is equal to 1 by x, and once you do the substitution s is equal to 1 by x, you will get the polynomial in terms of x, and now you apply the Ruth array for p of x, and then that 0 won't occur in the first column. I usually apply this technique. So if there is a 0 first element in a row, you replace that 0 by an infinitesimal delta, and then complete the array with the elements with some of the elements having delta, because instead of 0 you are using delta. And then you look at the signs of the elements above and below delta, because if both the signs above and below are the same, then what that means is that a purely imaginary conjugate root pair is occurring for the system. If there is a sign change, well, then the number of sign changes is equal to number of right half plane poles, as usual. The other alternative, of course, is to replace s by x inverse in the characteristic equation polynomial, and re-express the characteristic equation polynomial in terms of x, and then apply the Ruth array to the polynomial in x. Sometimes what happens is, the entire row is 0. You encounter a 0 row. When will you encounter a 0 row? When 1, 2, suppose there are 2 rows. These 2 rows are identical. Then this times this minus this times that divided by this, that will be 0. This times this times this times that divided by this guy will again be 0. So if the two previous rows are identical, then the next row is bound to be 0. Now if you encounter a row of zeros, then what is done is, so let us say this is the ith row, and let us say it's a bunch of zeros. What you do is, then you look at the I plus 1th row, and it will have some elements. Let us say the elements are A, B, and C. And let us say this I plus 1 is, well, let's see. Usually, almost always I plus 1 will be an even number. So let's take an even number. Let's say this is, well, if it's an even number, s to the power 4 to so let's say this is 4. So then it will be then you prepare the what is called the auxiliary polynomial corresponding to the row above the 0 row. So the auxiliary polynomial p is equal to a times s to the power 4 plus b times s square plus c times s to the power 0, which is essentially c. This is the auxiliary polynomial. Auxiliary polynomial. And then what you do is replace the elements of the 0 row with the coefficients of the polynomial that you get after differentiating the auxiliary polynomial. So if I differentiate the auxiliary polynomial, I'm going to get 4a, 2b and 0, of course. And then you continue with the elements replaced by the derivative of the auxiliary polynomial. So this is the procedural aspect. These 0 rows occur because there are roots that are mirror images of each other. So roots that are mirror images of each other would be of the form, for example, plus a minus a. That's a mirror image root, mirrored about the y-axis. There could also be a root that is plus bj and minus bj. That's mirrored about the x-axis. So whenever you have these 0 rows, what that means is there are roots that are occurring as mirror images of each other, and this is not complex conjugate root pairs. This is, I think this should be replaced with mirror images, and mirror images are of a certain kind. You could have mirror image around x-axis or real axis, or mirror image about the imaginary axis. Mirror image roots. That is why you get. So roots are occurring in pairs that are mirror images, and because roots are occurring in pairs that are mirror images, therefore the auxiliary polynomial is always of even degree. Because if there are 2 roots that are mirror images, then the degree of the polynomial is going to be 2. If there are 2 pairs of roots, then you've got 1, 2, 3, 4 roots, so that the degree of the polynomial is going to be 4. Auxiliary polynomial degree is going to be 4. If there are 3 pairs of roots that occur as mirror images, then the degree of the auxiliary polynomial is going to be 6. So auxiliary polynomial will always be of even degree, and again this needs to be mirror images. Okay, so that's that. Now let's just go through some examples. And please have your calculators with you. I have worked it out previously, and I'll just throw the numbers. So let us say the characteristic equation is this. So how do we build the root array? Highest power is 5, so we will start with s to the power 5, and we will have the coefficients 225, alternate coefficients, and 15. And you can see immediately 15 is common to this, so this is replaced by 8, this is replaced by 15, and this is replaced by 1. Let's make the s to the power 4 row. That's going to be these 3 coefficients. So that's going to be 120, 85 and 3. So now we start building the s to the power 3. What is this guy going to be? Let's call this b. So b is going to be 120 times 15 minus 8 times 85 divided by 120. So b is going to be, we'll call this b, is equal to 120 times 15 minus 8 times 85 divided by 120. and that's going to be 15 minus 8 by 120 times 85, and पाड़ा पड़ो यार 8 15s are right, and so then this guy is going to be 3s, and this guy is going to be 17s. So 15 minus 17 by 3. I did the calculation, whatever that is. So let me just take a look at that. That's 12.5516666, something like that. So this is going to be 12 point, approximately 12.52. So we get here 12.52. Let's call this element C. What is this element C going to be? The element C is going to be this times this minus this times this divided by this. So that's going to be 120 minus 8 times 3 divided by 120. So that's going to be 1 minus 24 by 120, and I'll check up पढ़ा पढ़ देते हैं. Yeah, so let's 6 4s are 24. In fact 24 का पूरा ही पढ़ा पड़ जाएगा ना. 24 5s is 120 minus 1 by 5. Oh, is that right? Hi. See, I made a stupid mistake, and the stupid mistake is as follows. This is 274, and therefore 274 times 15 minus 8 times 85 divided by 274, and of course this is going to be, ये सब काटा फाटा गलत है. 15 minus 8 by 274 times 85. If you do the calculation, this of course is correct. Over here this is going to be 274 times 1 minus 8 times 3 divided by 274, and therefore this guy is going to be 1 minus 24 by 274, and you do the calculation, the number that you should get is 0.912. Yeah, that's what you get. So C turns out to be 0.912. Nothing over there, so we'll just say it's 0. Now go to the S square row, and if you go to the S square row, this element is going to be this times this minus this times that divided by 12.52. I'm not going to make a fool of myself. I did the calculation and confirmed it, so this guy turns out to be 65. Slight mistakes in calculations are okay because you're not just interested in the sign of the. What is this element going to be? This element is going to be this times this minus 274 times 0 divided by, so this is going to be 3. Okay. Now we come to the s to the power 1 element. So that's going to be this times this minus this times this divided by, and since you are dividing by a large number 65, this number is going to be small, and it turns out to be 0.335. Forgive my eyesight. And finally s to the power 0 element is nothing but 3. because this times this minus this times 0 divided by this guy leaves 3. So now if you look at the first column of the root array, all the elements are positive. Because all the elements are positive, there are no sign changes, therefore there are 0 RHP planes, RHP roots. Poles implies system is stable. Okay, so that's that. Zero sign changes, therefore zero right half plane roots, therefore stable system. Let's look at another example. This time the other coefficients are the same, except that I've made this 5, and therefore the coefficients are going to be what they are going to be. What was this? This was 8, 15 and 1 after cancelling, after taking the factor of 15 out. This guy is going to be 274, 85 and 5, and I can immediately tell from previous this guy is going to be 5, and maybe this guy is going to be 5. No change here, because so this guy is going to be 12.52 as before. This times this minus this times this, you are subtracting a larger number, so there will be some change here. So it's going to be 274 minus 40, 8 5 is a 40 divided by 274. So that's, so let me call this A. So A is equal to this guy, and that's equal to 1 minus 40 by 274, whatever that is. I have done the calculation, 0.854. So this guy is 0.854. The S square term is going to be, this term is going to be this times this minus this times this divided by this guy. So that's going to be, let me call this B. So B is going to be equal to 85 minus 274 times 0.854 divided by 12.52, and do this calculation and get B, and it turns out that this term is 66.31. Yeah, so B turns out to be 66.31, and yeah, this guy, this times this minus this times 0 divided by that guy leaves 5, so 5 just gets copied down there. What do we have here? This times this minus, 12 5s are 60 of that order, yeah, and 66 times 0.85 will be of the order of 60, and so now we are getting very close, so we got to do this calculation accurately, and it turns out that this guy is actually minus 0.09. And now if you examine your first column of the root array, there is one sign change in going from here to here, so that's 1, and then there's another sign change in going from here to here, so that's another 1. So there are a total of 2 roots in the right half plane, and therefore the system is unstable. So just a quick summary. This is the root array calculated as quickly shown. and because of the sign change in going from here to here and in going from here to here, there are two sign changes, therefore there are two roots in the right half plane, and therefore the system is unstable. Example 3. So now actually this is 57096 or something like that. Yeah, but for the purposes of illustration, I think this is just fine. Here what you will find is, if you go through the procedure, and I am not going to repeat the procedure because that will bore you, this guy turns out to be 0, and because this guy turns out to be 0, you do delta times this minus this times this divided by delta, so therefore this guy gets copied over here, and that completes the root array. And what you find is that if I look at the signs above, all positive. If I look at the signs below, all positive. That means there are no right half plane roots. If I look at, now this could be treated as a 0 row, and the auxiliary polynomial is 66.03 s square plus 4.571, and if I get the roots of this auxiliary polynomial, I'll have xs is equal to 4 minus 4.571 divided by 66.03 square root, which is going to be plus minus j times, and I think I did the calculation but I forgot to write the root. Doesn't matter, so we will just 0.2631. Yeah, j times 0.2631. So the auxiliary equation gives these two mirror images as roots of this characteristic equation, and you can see that because these two roots are purely imaginary, system is on the verge of instability, sustained oscillations. So there are no right half plane roots, but there are these two roots that are on the imaginary axis, 0.2631j minus 0.2631j, real axis, imaginary axis. There are other roots, they are all in the left half plane, they are all over here, but these two roots are on the border. If this characteristic equation has been obtained for a particular value of kc, if I crank up kc above that value, then these roots will go into the right half plane and you'll get system instability. Okay, so that's that. So no right half plane root, two purely imaginary root pair, therefore system will exhibit sustained oscillations. Example 4. Man, I've got so many examples this time, very unlike me. That's why it took so long to prepare these examples. Here's another one. By the way, you see there's a sign change. If there is a coefficient sign change, if there are coefficients that are all positive and then one of them is negative, immediately you can tell that at least one root is in the right half plane, system is unstable, guaranteed. So it is a necessary but not sufficient condition. If let us say all the coefficients are positive, then can't really tell. So for example, in the previous example, let's just go back a little bit. I'm going forward, forget. Okay, when this was 4.571, I had sustained oscillations. When this thing was 5, I had an unstable system. That means the controller gain that gave me this resulted in those two roots going into the right half plane. And when this guy was small, I had a stable system, none of the roots in the right half plane. This goes to 4.571. I got two roots that are purely imaginary, and then this goes to 5, and then I got um, two roots that are in the right half plane. Yeah, so this is what my root array analysis is telling me for this system, with this guy, this coefficient changing, perhaps because we are changing a controller tuning parameter. Okay, so let's see, what was I trying to say? Look at this guy. So because you've got a sign change here, guaranteed this is going to be unstable. Only issue is how many roots in the right half plane, that we'll figure out. But guaranteed this is going to be left half, at least one root in the right half plane. By the way, look at this guy, all coefficients are positive, yet it is unstable. So change of sign is a necessary, but not change of sign. A negative coefficient in the characteristic equation is a necessary but not sufficient condition. You can have systems that have all positive coefficients in the characteristic equation and yet they can be unstable. This is one such example. Root array is the necessary and sufficient condition. If all the elements of the first column of the root array are not exhibiting any sign change, have the same sign change, then that characteristic equation is stable, or the system corresponding to that characteristic equation is stable. Oh, let's see, where are we now? Example 4. So this is guaranteed to be unstable. So ये तो आँख मीच के बोल दो ये. You just close your eyes and say this is guaranteed to be unstable. This is unstable. Okay, now next. By the way, as an exercise, I'd like you to show that if there is a negative coefficient in the characteristic polynomial, there's at least one root in the right half plane. Can you show this, prove this mathematically? Do this as an exercise. Okay, root array. Okay, so if you prepare the root array, this guy, s to the power 5 is going to be 1, 3, and minus 4. S to the power 4 is going to be 3, 9, and minus 12. 3, 9, and minus 12. And you can immediately see I take one common, and this is what? Minus 4. And you can see that you have two identical rows, and therefore this guy is going to be 0, 0. So you got a 0 row. So auxiliary polynomial is going to be one s to the power 4 plus 3s square minus 4 . This is the auxiliary polynomial, and by calculating the roots of this polynomial, I'll get those mirror image root pairs, and because this order is 4, there will be two root pairs that are mirror images. And let us just calculate those two root pairs right now from this. So replacing s square by x, so what you get is x square plus 3x minus 4 equal to 0, and the roots are going this factorizes by itself, no? X plus 4 into x minus 1 equal to 0, and is that right? 4x minus x, that's 3. Yeah, so this factorizes by itself, and therefore what you get is x is either is equal to minus 4 or it is equal to plus 1, and x is s square, and therefore this guy implies s is equal to plus minus 2j, and this guy implies s is equal to square root of 1, that is plus minus 1. So these are the 4 roots, 2 root pairs that are mirror images. They are mirror images in this way, plus 2j minus 2j plus 1 minus 1. You can see this plus 1 will create instability. This is in the right half plane, so this will create instability. Yeah, implies creates instability. Okay, so that's that. Yeah, I've written all this, so we gotta remove all this. We've got the roots, and once we've got the roots, okay, so the auxiliary polynomial is this guy. Derivative of p prime is actually 4s cube plus 3 to the 6s. So the elements here, replace these 0 elements by 4 and 6, and 4 and 6 have got 2 common, so I can, maybe I should, just for completeness, I should say 4 and 6, and you take 2 common, so this will be 2 and 3, and therefore s square element here is going to 2 3s are 6. 6 minus 3 divided by 2, so that's 3 by 2, and this guy is 2 minus 4, and so this guy is going to be minus 4, and s to the power 1 is going to be 3 by 2 into 3. How much is that? 3 by 2 into 3 minus 2 into minus 4, so that's plus 8 divided by 3 by 2. अरे यार अब इसको calculate करो. It's really not important because this is going to be a positive number, and then this guy is going to be this times this minus s, so this guy is going to be minus 4. So you can see that all the elements here are positive. Not all, there is one change of sign, so there is one right half plane pole which is causing instability, and we saw that that right half plane was s is equal to plus 1. We got that from the roots of the auxiliary equation. Okay, so yeah, so 8.33 is what it came out to be. Okay. So we got these two as the mirror image roots from roots of the auxiliary equation or auxiliary polynomial. This is a fifth order system. We got 4 roots, 2 mirror image pairs, that's 4 roots. Remaining root, if you just divide and do factorization, you'll get s equal to minus 3 as the other root. So the polynomial that's written over here factorizes into this guy. Okay, so that's that. One change of sign in the first column, and therefore one right half plane root, which is this guy s, sorry, which is this guy, s equal to 1. So you got an unstable system. Oh, example 5, done many examples, huh? Oh yeah. So this is the design, not design kind of example. When do we go unstable? You see, root array, the first if the characteristic equation is for a closed loop system, the closed loop system will have Kc in the characteristic equation, and as Kc is changed, the characteristic equation coefficients change, or at least some of the characteristic equation coefficients change. And because the characteristic equation coefficients are changing, therefore some of the elements of the first column of the root array will change, and one can then calculate that value of Kc where the element becomes 0, because when the element becomes 0, that corresponds to purely imaginary roots conjugate pairs, which is that the system is on the verge of instability, the system exhibits sustained oscillations. Okay, so that gives us a limit or a critical value of the Kc beyond which the closed loop system is going to be unstable. So let's look at this guy. 1 2 3 4 5. 1 2 3 4, 5. So this guy is controlled using a peak controller. Use the Ruth array to obtain the controller gain range for which the closed loop system is stable. Also obtain the frequency of oscillations at the verge of instability. So we know that the closed loop characteristic equation is 1 plus GPGC equal to 0. And for a what is it called? For a proportional controller, GC is equal to KC. So therefore what we have is 1 plus 5 divided by S plus 1 times 2S plus 1 times 3S plus 1 times 4S plus 1 times 5S plus 1 times Kc. This guy is equal to 0 is the characteristic equation, which essentially solves to S plus 1 times 2S plus 1 times 3S plus 1 times 4S plus 1 times 5S plus 1 plus 5 Kc is equal to 0. And if you do the math, you'll get the same coefficients as this guy. So what are the 120, 274, 225, 85, 15? So well, so this is going to be 120 s to the power 5 plus 274 s to the power 3 plus 225 s to the power 2 plus 85 times s plus 1 plus 5 Kc equal to 0. So this is the characteristic equation, and you can see that this coefficient, the s to the power 0 coefficient of this polynomial, is a function of Kc, the controller tuning parameter. So now if I build the Ruth array, yeah, so this is what I get. If I build the Ruth array, let's just build the Ruth array. And s to the power 0 is going to be this term. We've seen that, so I'll call this guy alpha. Okay, so s to the power 0, we're going to get simply alpha. S to the power 0 is going to be alpha. So as usual, this is going to be 8, 15 and 1. This guy is going to be 274, 85 and alpha. This guy is going to be 12.52 as we got before, and this guy is going to be what is this guy going to be? 1 minus 8 by 274 alpha. And 8 by 274 I think turns out to be 0.0292. We'll have to see. 0.0292 alpha. This guy is going to be C. This guy is going to be, I think this times this guy is going to be simply alpha, and this guy is going to be, I'll call this D. Okay, and we'll call this E. So what is D going to be? D is going to be equal to 12.52 times 85 divided by 12.52. So that's 85 minus 274 times 1 minus 0.0292 alpha divided by 12.52, so that's going to be 85 minus 274 by 12.52, and you can see 12, 20, 20, 12 will 12 times 20 will give you 240, 12, 12.5. Yeah, so this is going to be about 63, plus 274 by 12.52 times 0.0292 alpha. And if you do the calculation, which I have done, and the polynomial is going to be somewhat complicated, but that's besides the point. So the polynomial turns out to be 63.112. This minus this comes out to be 63.112, plus the other guy turns out to be 0.6391, 0.6391 alpha. Okay, so that's what I'm going to write over here instead of D. So that's 63.112 plus 0.6391 alpha. And then this element E is going to be this times this minus this times this divided by this. So E is going to be minus 12.52 alpha divided by 63.112 plus 0.6391 alpha. And you will see that this guy turns out to be, it will be a quadratic in alpha, and that quadratic I have calculated, and it turns out that this guy is, and let me call this so this was, we were calling this D. So this guy turns out to be minus 0.0187 alpha square minus 13.7219 alpha plus 63.112 divided by D. Note that because Kc is positive, therefore alpha is positive, and therefore D will, by the way, this is plus, D will always be positive. Now the question is the numerator going to be positive? Because this number is positive, this is positive, this is positive, alpha is positive. So we got to make sure that the s to the power 1 coefficient is always positive. This guy is always positive. Yeah, so all the coefficients except the s to the power 1 coefficient needs to be ensured that it is positive. And note that as Kc is increased, alpha increases. As alpha increases, alpha square will increase. So the negative term will increase as alpha is increased, and there will come a stage when the negative term becomes exactly equal to 63.112, and in that case the coefficient in the s to the power 1 place will go to 0, in which case we will have purely imaginary conjugate roots, which corresponds to verge of instability. And this corresponds, the verge of instability corresponds to the alpha that satisfies this characteristic, that drives the quadratic to 0, and using the quadratic formula you can calculate alpha, and alpha turns out to be, I think there are two values of alpha. One of them is very large negative, minus 738, minus 738.36, and the other is plus 4.5709, 4.5709, and you remember this 4.571, this is exactly that guy. And this one is rejected, this one is accepted. If you accept this guy, then for alpha is equal to 4.5709, the auxiliary polynomial is going to be d times s square plus 0.6391 alpha is equal to 0, and therefore s is going to be plus minus square root 0.6391 alpha divided by d times j. Yeah, because when you take this guy to the right hand side, negative sign comes, and when you take the square root of -1 you get j. And if you do this calculation, it turns out that s is equal to plus minus 0.2631 j. You can do this calculation and confirm for yourself. So this is the Ruth array, and by finding the roots of this quadratic, we get that alpha should be less than 4.5710, because if it goes above 4.5710, this guy goes negative, and this corresponds to a Kc of 0.714. So for Kc less than 0.714, you have a stable system. At the verge of instability, the auxiliary polynomial is this guy, and therefore I calculated the value of d for alpha is equal to 4.5710. You substitute that value of alpha here, and then what you get is d is actually 66.0327327, and therefore from this you get, and therefore the frequency, because the roots that cause sustained oscillations are here, and this is 0.2631 and this is minus 0.2631. So you will get a sine term or a cosine term which will have 0.2631 j t. So it will be a sine wave of frequency 0.2631, and by default I take the units for chemical systems in terms of minutes, electrical systems would be seconds. So 0.2631 radians per minute is the frequency of oscillation. So this completes the Ruth array examples. Now let's continue. As we have seen, as you crank up the gain, the roots, or at least some of the roots of the characteristic equation, move towards the right half plane. At a particular gain, you will have two roots on the imaginary axis, two purely imaginary roots, complex conjugate pairs. These roots are now on the verge of instability. If you crank up the gain further, the root will move, these two roots will move into the right half plane, and that will cause instability. So the controller gain proportional controller gain for which you get two purely imaginary roots of the characteristic equation which cause the system to oscillate in a sustained manner, which cause sustained oscillation in the system. That particular controller gain is called the ultimate gain for the system. Proportional controller gain, not PI, not PID, but a P only controller gain. And the period of oscillation is known as the ultimate period. So ultimate gain is the proportional controller gain for which sustained closed loop oscillations occur. Ultimate period is the period of those sustained oscillations. And Ku, Pu sort of tell us that look, the gain should not exceed this value, because beyond this value you're going to get instability, so stay away. It draws a red line. And so Ku and Pu are used for empirical tuning. Empirical meaning experience based tuning. And just to drive home the point, I just simulated a system where the green line is Kc much smaller than Ku. The cyan line, this guy, is for Kc about 1/4 of ultimate gain. The magenta line is for Kc about half of Ku. The black line corresponds to Kc being exactly Ku, and you can see that now you are getting sustained sinusoidal oscillations, and this is for a servo response. And then as we have the red dotted line, this is for Kc being slightly above Ku, and you can see that now the oscillations are blowing up. So this is typical of feedback control systems. For low gains you get a smooth non-oscillatory kind of response. Crank up, then you start seeing oscillations, and then those oscillations take longer to die out, and then you get sustained oscillations, and then those sustained oscillations start to blow up. So that means that the damping coefficient of the system initially was greater than 1, then it became less than 1, and then it became 0 corresponding to sustained oscillations, and then it became negative corresponding to oscillations blowing up. So this is typical. And so this gain of a proportional controller for which you get sustained oscillation plays a crucial role in controller design. And electrical engineers will do a very simple thing. They'll hook up an oscilloscope to the system, crank up the gain just like you crank up the volume knob on a speaker. Crank up the gain, and on the oscilloscope you'll start getting oscillations, and once those oscillations become sustained, you say, oh, this is the gain at which my system goes unstable. Rule of thumb tuning is, okay, what gain should I use? Make it half. Okay, so I'm away from instability by a factor of 2. That's what electrical engineers do. Chemical engineers don't have this liberty. And for chemical engineers, and in fact electrical engineers also, people have looked at S-shaped open loop response kind of systems, and tuned all kind of systems, and tried to come up with a rule that gives decent tuning for most such systems, most lag dominant systems. What is a lag dominant system, by the way? Lag dominant system is like this. Give it a step, you get a response. A lag dominant response would be small dead time, and then it takes that's a lag dominant response. There is a dead time is small. What is a dead time dominant response? Dead time dominant response would be, you give it a step, nothing happens for quite a bit, and then suddenly things take off. So this is lag dominant. System. This is delay or dead time dominant system. Okay, so these empirical tuning rules are rules that give us, I would call it a rule because they may or may not work, it depends on the system, but they are usually a good starting point for tuning your system. So they give us Kc, tau I, tau d that are a good starting place, and these Kc, tau I and tau d are given in terms of Ku and Pu. Kc is given in terms of Ku, and tau I and tau d are given in terms of Pu. Pu is the ultimate period, and these are experience based tuning rules. That's why they're called empirical. most commonly, the most popular of them, one of them is Ziegler-Nichols. Ziegler-Nichols developed this rule for quarter decay ratio in the regulator response in typical lag dominant systems. So Ziegler-Nichols is for aggressive control. That's why quarter decay ratio, that means the damping coefficient would be of the order of 0.21 or 0.205, something like that. So Ziegler-Nichols tuning is recommended when we want aggressive control. For example, in an exothermic reactor, we want to control the temperature aggressively, because if the temperature rises, the non-linearity can cause a reaction run away. So you want aggressive tight control of the temperature. Maybe Ziegler-Nichols is useful there. But in chemical processes, we want, gentle, tender, loving kind of manipulation. We don't want extremely harsh manipulations, because that can damage the equipment, that can create unsafe situations. Anyway, we are dealing with hazardous substances. So tender, loving, care kind of control is what we want, and for that there's the Tyrrell-Lieben tuning rule. It is used on most process systems for gentle changes in the manipulated variables that assists or that facilitates smooth operations, not too many bumps, a non-bumpy ride. Okay, what are these tuning rules? Well, this is the Ziegler-Nichols tuning rule. So you get the KU-PU. For a P only controller, the recommended KC is whatever is the ultimate gain at which you go unstable by half. For a PI controller, you back off further, divide by 2.2. For a PID controller, because the derivative action helps stabilize the system, you can have higher gain, and so you're backing off by only a factor of 1.7. The tau I in a PI controller is about the ultimate period. The tau I and tau D in a PID controller are as stated here. On the other hand, the Tyrrell-Lieben tuning rule, you can see it is, much less or significantly detuned from the Ziegler-Nichols gain, significantly higher reset time, and so these very conservative tunings actually ensure gentle manipulation. So you get there eventually, slowly but surely. Tyrrell-Lieben is for a lag dominant process. There's also Kyankon-Marlin for dead time dominant processes, and the rule is in front of you. Maybe when we do internal model control, if we do it, we can do the derivation of these two tuning rules. Okay, these can be derived from transfer functions. So maybe we will do that either as a demonstration or as an exercise. So these are tuning rules. So now let's just start doing some synthesis problems where we want to design a controller for a particular kind of. So here's a process transfer function, CISO process transfer function is given. Calculate KU, PU, and then obtain the Ziegler-Nichols settings for P, PI, and PID controllers. How do we do it? What's the closed loop characteristic equation? The closed loop characteristic equation is actually 1 plus GCGP is equal to 0. For a proportional controller, GC is equal to KC, so therefore we have 1 plus KC times 2 divided by 2S plus 1 times S plus 1 into half of S plus 1 is equal to 0, and therefore we get 2S plus 1 into S plus 1 into half S plus 1 plus 2 Kc is equal to 0. And now you got to open this thing, so this is going to be 2S square plus 3S plus 1 times half S plus 1 plus 2 Kc is equal to 0, and this is going to be 2S square into half of S, that's S cube, plus 3 by 2 S square plus 2S square. So 3 by 2 plus 2 is 2 2s are 4 plus 7 by 2 plus 7, so 7 by 2 S square plus 3s plus half s. So 2 3 so that's also 7 by 2. So 7 by 2s plus 1 plus 2 kc equal to 0. So that's the closed loop characteristic equation. So this is the closed loop characteristic equation. And for Ziegler-Nichols or for KU-PU, we are looking for those roots of this characteristic equation that are purely imaginary, because when you have purely imaginary roots, that's when you get sustained oscillation, complex conjugate pair. So for KU, so at Kc is equal to Ku, S is equal to j omega, a purely imaginary root, must satisfy CLCE. And now that this is satisfying the CLCE, what we do then is so this must satisfy this equation, and therefore what you get is omega cube times minus j plus 7 by 2 omega square, and j square would be minus, so this would be minus, plus 7 by 2 j omega plus 1 plus 2 kc, that's equal to 0. And if you now look at this guy, collect the real and imaginary terms in one location, so you will have the real terms are 2 kc plus 1 minus 7 by 2 omega square, and the imaginary terms are, we can take j omega common, and so what you get is, if you take j omega common, you'll get 7 by 2 minus omega square equal to 0, and therefore the real part and the imaginary part must go to 0. So from the imaginary part must being 0, we get omega is equal to square root 7 by 2 radians per minute at Ku, and therefore Pu is going to be 2 pi by omega, which calculates to be 3 point something, let me see, 3.36, this calculates to be 3.36 minutes. So the ultimate period is 3.36 minutes, and from real part going to 0, we get Kc is equal to 7 by 2 omega square minus 1, this whole thing divided by 2, and if you substitute, you see omega square itself is 7 by 2, so 7 by 2 times 7 by 2 is 49 by 4 minus 1, 49 by 4 minus 1, so that's 45 by 4, so that's 45 by 8. So Kc is equal to 45 by 8, which is equal to how much? 8 5s are 40, 8 6 are 48, 28 2s are 5.625. So ultimate gain is 5.625, and ultimate period is equal to 3.36 minute. And now we can apply the Ziegler-Nichols tuning rule to obtain KU-PU. Just look up the table and do those things. I will not do that and waste your time. I'll simply present the results. So in summary, we obtained the Closed loop characteristic equation for ultimate gain for sustained oscillation, S equal to j omega must satisfy the characteristic equation. So you substitute S equal to j omega into the characteristic equation and then simplify into a real part and a imaginary part, and the real part and the imaginary parts must go to 0, and that gives us uh, an ultimate period of 3.36 minutes and again ultimate gain of 5.625, and corresponding to this the Ziegler-Nickel tuning is in front of you. That's this example. Now let us look at another example where what we want to do is we have the same process, same proportional controller, it's just that now we are going to tune for a closed loop damping coefficient of this guy 0.7071. That means we are tuning for chi is equal to 1 by square root 2. Notice that when chi is equal to 1 by square root 2, we know that phi or tan phi is equal to imaginary part of the root magnitude divided by real part of the root magnitude, and that is equal to square root 1 minus epsilon square divided by epsilon. And if you put epsilon is equal to or chi is equal to 1 by square root 2, what you will get is actually tan phi is equal to 1. That means the real and imaginary part magnitude of the magnitude of the real and complex parts of the dominant roots of the characteristic equation must be the same. So that means S is equal to minus a, and I'm explicitly putting a minus so that it's a left half plane root because we are not interested in an unstable, plus ja must satisfy the closed loop characteristic equation, and therefore now what we have is S cube plus closed loop characteristic equation as before is this guy, and now in this guy we substitute S equal to minus a plus ja, and then what we will get is minus a plus ja whole cube plus 7 by 2 into minus a plus ja whole cube plus 7 by 2 into minus a plus ja plus 1 plus 2kc is equal to 0. And if you do this guy, this will turn out to be, do the algebra, maybe I should do the algebra, minus a cube plus 3a cube times j minus 3a times ja whole square, and j square will give us a plus, yep, minus ja whole cube plus ja whole cube, which j square will become minus, and then you'll be stuck with a cube j plus 7 by 2 times, so this comes from the cube. This guy is going to be a square minus 2a square j plus ja whole square, which is going to be minus a square. These two guys cancel out. Well, plus 7 by 2 aj minus 7 by 2 a plus 2kc plus 1 equal to 0. That's so what we get here is 2a cube minus 2a cube minus or plus plus 2a cube j minus 7a square j, that's this guy, plus 7 by 2 aj minus 7 by 2a plus 2 kc plus 1 is equal to 0. Collect the real and the imaginary terms. So real terms are 2 kc plus 1 minus 7 by 2a plus 2a cube, and the imaginary terms are, I'm going to take aj common, 7 by 2 minus 7a plus 2a square equal to 0. And then we say that okay, solve this quadratic to get a. So what we get then is a is equal to minus b square minus b by 2a. A is equal to seven by 4 plus minus square root 49 minus 4 times 4a times c divided by 2a, which is 4. This guy goes, and so what we get is to 7 by 4 plus minus, what the hell is this, man? 49 minus 28, so that's 21. And if you look at these two roots turn out to be, I think I've done the calculation. Where are these two roots? So these two roots turn out to be, so therefore what we get is a is equal to, there are two roots, 2.8956 and the other guy is 0.6044. And if you apply this to real part going to 0, you'll get kc, and we get two values of kc, and those two values of kc are, one of them turns out to be negative and the other guy turns out to be positive. Obviously we are not looking for positive feedback, so we want negative feedback, so this is the value that gets accepted. So that's the controller gain for a closed loop damping coefficient of this much. And at this closed loop damping coefficient, at this gain, S equal to this guy minus 0.6044 plus J times 0.6044 plus and minus. These two are roots of the characteristic equation. So to summarize, we write the characteristic equation, and then as I explained, for a damping coefficient of 1 by square root 2, S equal to minus A plus AJ must satisfy the closed loop characteristic equation. And then when we substitute and do the necessary algebra, we get a real part and a imaginary part, and both of these must go to 0. And from the imaginary part going to 0, we get, by solving the quadratic for the imaginary part going to 0, we get two potential values for A. For these two potential values of A, when we calculate Kc using the real part going to 0, we get two candidate values of, this is not Ku, this should be Kc, two candidate values of Kc, and these are this and that. This is not acceptable because this will lead to positive feedback, so this is the accepted value, and thus we get Kc equal to 0.3369, as the controller gain, for which we get a closed loop damping coefficient of 1 by square root 2. And now I'm going to crank up the speed a little bit because doing calculations for everything is going to take time. So I'm just going to explain the procedure because I'm losing my patience now, and I'm sure you are too. So now what we want to do in this example is we want to design a PI controller where tau I has been chosen to cancel the dominant open loop pole. What do you mean by dominant open loop pole? Dominant is the one that is the slowest. That means largest time constant. This is the open loop transfer function. This is the time constants of 2, 1 and half. 2 is the largest. So what this implies is I'm going to use tau I is equal to 2. If I use tau I is equal to 2, then my 1 plus GPGC equal to 0 will become 1 plus 2 divided by 2s plus 1 into s plus 1 into half s plus 1 into PI controller. So there is Kc, there is tau I s, and tau I is equal to 2 is what I'm using, 2 minutes. So 2s tau I s plus 1 divided by tau I s, so 2s. These two cancel out, 2 cancels out, and therefore what I get is 1 plus, the characteristic equation turns out to be s plus 1 into half s plus 1 into s plus Kc equal to 0, and that will turn out to be half s cube plus 3 by 2 s square plus s plus Kc, which is actually s cube plus 3s square plus 2s plus 2Kc is equal to 0. So we are going to work with this characteristic equation. That's the characteristic equation that we get. And again, s equal to minus a plus aj must satisfy the closed loop characteristic equation. Substitute this into this guy, do the necessary algebra, separate the terms into an imaginary part and a real part. That's what you get. Imaginary part must go to 0. Real part also must go to 0. Imaginary part is a quadratic. This quadratic can be solved. By solving this quadratic, I get two candidate values for a. For these two candidate values, if I substitute into the real part going to 0, I get, this should not be there. I get Kc, and Kc turns out to be this or that. This one is rejected because we want negative feedback, not positive feedback. So this is the Kc. So Kc equal to 0.3262. Notice that this is less than the Kc that I got for proportional control. Now we go to example 4. We're going to design a PID controller where tau I and tau D are chosen to cancel the slowest and the fastest poles respectively. Slowest pole is this guy, fastest pole is this guy, and therefore we are going to set tau D is equal to half and tau I is equal to 2, and of course the time units are minutes, and therefore 1 plus GPGC equal to 0 will turn out to be 2 times Kc times 2s plus 1 divided by 2s. That's a PI controller times tau ds plus 1. Tau ds plus 1 would be half s plus 1 divided by 1 by alpha tau ds, and alpha will take as 1 by 10. So 1 by 20 s plus 1, and multiply this by Gp. What do we have for Gp? 2 I have already taken, so 2s plus 1 times s plus 1 times half s plus 1. This guy cancels by design. I chose my tau I and tau D to do that. And this guy plus 1 should be equal to 0. That's my characteristic equation. So what I get is 2 and 2 cancel out. So what I get is s plus 1 into s into 1 by 20 s plus 1 plus kc is equal to 0. Multiply by 20. So if I multiply by 20, this will become 20, and this will become 20, and so what I will then get is s cube plus 21 s square plus 20s plus 20 kc is equal to 0, and again the usual dingbat, s is equal to minus a plus aj must satisfy this guy. Do the necessary algebra. If you do all of that, here's my characteristic equation. S equal to minus a plus aj must satisfy the characteristic equation. Do the necessary algebra. This is the real part, that's the imaginary part. Each of these must go to 0. From the imaginary part going to 0, we get two candidate values of a. For these two candidate values of a, from the real part going to 0, we get kc as this and that. This one is rejected, this one is accepted, and therefore kc equal to 0.4759 gives me a closed loop damping coefficient of 1 by square root 2. Notice that this is much larger than the P and the PI controllers, and you see that is how you get more aggressive control by using derivative action. I just obtained dynamic servo and regulator responses. For the regulator I just assumed that the disturbance is at, I just assumed that this is U, disturbance is entering here, and this is GP. That's what I assumed my process to be, and then you're putting in a GC over here, no? Plus and minus. So that's what we are doing, and this guy is Y. I obtained the responses. The regulator response unit step, you can see if you take no control, Y deviates from 0 to 2. If you put in a P controller with the I think 0.33 0.3262 was the controller gain that we got, you can see that the deviation away, the deviation away from set point is mitigated, but it doesn't get back to set point. There is an offset. By the way, you can calculate this offset by using the final value theorem to figure out what the final value of y is going to be. Final value theorem can be applied. If you use integral action, you can see the magenta curve is for a proportional integral controller. What is this? PID controller. So you can see that the control for PID is actually tighter. You'll get much lower integral absolute error. For the servo response, this is for a P controller, this is for a PI controller, and this is for a PID controller, and you can again see the PID controller is actually has got a much faster, smaller rise time. Of course, the overshoot turns out to be a bit more than expected, but then these are not optimized settings. We did not adjust the value of tau d to get the best possible setting. But the point is, PID controllers will generally give more aggressive controller tuning. With this, we come to a summary of this rather longish lecture. In this lecture, we have looked at dynamic system analysis and also design for dynamic performance specification. Ruth array is a very simple tool for determining system stability. It can also be used for finding out the limiting value of the controller gain beyond which the system goes unstable. Ultimate gain and ultimate period are of fundamental importance in the design of feedback controllers. These correspond to a P controller gain at the verge of instability for which you get complex conjugate purely imaginary roots which result in sustained oscillations. Once we have an estimate of Ku and Pu, this Ku and Pu can be used in empirical tuning rules for controller tuning. In controller design, Kc is adjusted so that the dominant closed loop pole pair has the desired closed loop damping coefficient, and the controller design, whether you are calculating ultimate gain or ultimate period, or you are trying to force the dominant pole pair to have a particular closed loop damping coefficient, all of this is governed by complex algebra on the closed loop characteristic equation. So the closed loop characteristic equation has a central role in controller design. With this we come to this end of this lecture. The midsem will cover questions related to material covered till the end of this lecture. Thank you for your patient listening to the lecture. Thanks again. Thank you for your time. Good day and goodbye. Let's call it quits.